All right, so everyone, can I have your attention, please? So we're about ready to start for the afternoon. So this afternoon, we're going to be looking at double variable analysis. So this morning, we looked at analyzing single variable data sets. Now we'll compare two of them. So two-variable analysis aims to establish relationships between multiple variables rather than simply analyzing what one will do. So brightness and time of day. If you can imagine a graph of the brightness versus the time of day, it makes sense that there is a relationship between those two because of the definition of a day, as in the rotation of the Earth. And the most useful tool for it is a scatter plot. So we've already covered scatter plots in the morning, so I can very briefly go through what we'll do for that. So this is another activity. So open up the two-variable analysis Excel sheet. And that's in your shared folder again. So I'm going to give it a sec to load. You should see something that looks like this. So since you all already know how to create a scatter plot, we won't have much need to redo that. But just to remind you, it's an insert chart scatter, and then you will select the data and select the x and y values. So what you can see here is currently it's in the Nonlinear tab. Head over to the Correlation tab. That's the first worksheet on the bottom. Do you all see? Yep, OK. And we can see a scatter plot between the x and the y data. So these, you'll notice, tend to be fairly linearly arranged. And you can also hit F9 to reseed the data, and that'll give it a slightly different scatter plot. So again, we already know most of that, so we can quickly jump on to the next. So one example of a scatter plot based on time is bandwidth usage on school.ca. So school.ca is the engineering student website that the Engineering Society here at U of T runs. And this sort of applies to what AgOp was mentioning on Monday regarding cloud computing and how a traditional computing center has a certain capacity and it has varying demand, but the capacity has to stay the same. And that's something that you can see in this case. So this doesn't look like a scatter plot, but it actually is. It's just that we've taken our point. So for instance, this is a point here, and we filled it in green in the bottom. But it still is the exact same semantic value as a scatter plot. And so a couple interesting things to note about this. We see here that we have these peaks and then seemingly periodic valleys. Does anyone have any idea why those may be occurring? Yes.
Like if there's an update on the site or something.
OK. OK, so that's a good thought. Take a look at the time scale. How often do those peaks seem to occur? Yes? OK, right. So that's another thing that we can look at is the overall aspect. So yes, we do have a peak in exam season. That's because the school.ca website puts old exams online, as well as a slightly increased usage around the fall term exam season. But I'm thinking about these smaller peaks here. So we have one, then down, then one, then down. Senior? Exactly. Right? So people tend to use the school.ca more during the week, and we see a drop-off during weekends. We also see a drop-off here between or over the Christmas break because the university is closed then. And similarly, a lot less usage during the summer semester because most students don't take courses then. So that's just an example of how much data we can get from a scatter plot. And another thing you can note to tie it into the cloud computing lecture, that this peak here is the maximum bandwidth that school.ca has to handle. And that is what it's physically capable of handling. So that means that all of these other times, this area under this line here and the rest of the graph is wasted resources. So just to give you a real-life example of what AgOp was mentioning. So we can head back to our spreadsheets and start taking a look at correlation. So periodic relationships, like what I showed you with going up and down in weekends, tend to occur more when time is the variable. Other sets of variables where one of which is not time tend to have slightly different relationships. So positive and negative are two ways we qualify these, where one goes up, the other goes down. That's negative, and they both covary the same is positive. So for instance, if you are older, one common one that many of you probably have heard is taller people tend to have larger arm spans. In fact, the two values tend to be equal. Of course, they're not exactly equal, but they do have a very strong positive correlation. So arm span and height would look something like this. Can anyone think of any examples of where we might have a negative correlation? Earl, you can feel free to jump ahead and sit down. Can anyone think of any examples of where we might have a negative correlation? So variables where one variable goes up, the other might go down. Something like time spent playing video games and mark in class. That is a potential cause of that. Yes, a lot of people claim there's no correlation. And some studies vindicate that, others show otherwise, depending on how we define the parameters of it. But you can see how that might be. Sorry, yes?
Age and reaction time, driving reaction time.
That's a great one. Right, yes. So the older you get, the longer your reaction time gets. So that's actually positive because reaction time is longer with age, but you can also quantify it in terms of how reactive you are, which is inverse to that. So a couple of reasons that we might observe a correlation. One, and seemingly the most obvious, is causation. So in the case of what I got mentioned, the older you get, because of the various complications of senility, you tend to lose your ability to react quickly. So being older causes you to have less reaction time. Another is reverse cause and effect. So we could actually have what we think is being caused by one variable caused by another. So we'll look at an example of that in a bit. A third is common cause. So there could be some third variable that's affecting both. And in reality, those both are being affected by that and not affecting one another. And finally, coincidence. So coincidence is where the two happen to be going up or down at the same time, and there's really no relationship between the two except that they just happen to be doing that. So to give you guys a better understanding of these, we'll do a couple exercises. So I'm going to give you an example, and we need to figure out whether the correlation should be positive, negative, or no correlation, and why that is. So pesticide use and crop yield. Those are our two variables. Should they be positive, negative, or no correlation? Right. So the more pesticide use, the fewer pests, and therefore greater crop yield. Is that a causation effect, reverse cause, common cause? Any ideas? Yeah, so it is causing. The more pesticide use causes there to be a greater crop. Now here's a very interesting one. There was actually a quasi-study done that shows that shoe size tends to be positively correlated with performance on a standardized test. So the larger your shoe size is, means you'll perform better. Now I'm size 16. Does that make me a genius?
Yes, definitely.
No, okay, I'm asking. The correlation coefficient was actually very good. Yeah. Yeah, okay, Robbie's starting to come on to something here. He's asking what age group was this taken over? And the answer is it was taken over primary school children, so grade 1 to 6, whatever age that comes to. Yeah, so you've come across what it is that age causes shoe size to go up and also academic ability to go up the same. So since age is causing both, what is the reason for this correlation in terms of the terms that we gave on the previous slide? Yeah, common cause. So there is one interesting one. Now here's another one, total global cyclone energy and the Dow Jones. Do you all know what the Dow Jones is? Yeah, so it's a general or one company's way of measuring industrial stocks. Does anyone have any idea whether these should be positively, negatively correlated? Yeah, so that's the total amount of energy that has been released in cyclones around the world per unit time.
Foot size to height.
Pardon?
Foot size and height.
Foot size and height, yeah, that's definitely another one. So those, you could argue that those would be causal, in that more height means more foot size. You could also argue that's common cause because if you are have more of growth hormones, that'll cause you to both grow in height and in foot size. So depending on what you consider to be the ultimate root of the cause, there could be two possible causal links there. But regarding the global cyclone energy and Dow Jones, let's take a vote. Who thinks it's positive? Negative? A couple more? None. So we're about half and half between negative and none. I'm interested to hear from the negatives. Why do you think it's negative? John, I'm going to pick on you.
I feel like that if there's an increase in cyclone energy, there's probably a greater affected area, and which results in more money spent on helping it. So
Okay. Okay, so that's definitely a good way of looking at it. And that definitely would apply to other aspects of the stock market because of the nature of the Dow Jones looking primarily at large corporate enterprises that generally don't deal with things like disaster relief. That actually doesn't happen, but that's a great analysis. In reality, it is no correlation. That being said, if you take the data from the last 2 years, you'll find that they were both going up, and there is mild correlation, not a strong one, but a mild one between the two. Does anyone know why that positive correlation occurred? Right. So that's an example of coincidence. It just so happened that because we're recovering from the recession 4 years ago, the Dow Jones is still going up, and because, well, we don't really know why, but weather patterns being what they are, global cyclone energy has gone up, and that's just a coincidence. If you look at the past 100 years, though, there is clearly no correlation, or at least none of a nature that we can figure out. So now here's another one that we'll come back to. How frequently a student is tardy in his mark. What type of correlation should that be? Yeah, so it seems that if you're tardy more frequently, then your mark should go down. And that is the case, and we'll come back to why in a bit. The point that I want to really drive home here is that correlation does not imply causation. So what that means is just because two variables are correlated does not mean that one causes the other. So for instance, a simple example, I could say that studies have shown that celebrating more birthdays leads to a longer life. I think you can all see the fallacy there. So when you're doing your analysis for the final project, make sure to think about the data you get. Think about the correlation coefficients you get, and make sure that it makes sense that these two variables are causing one another, and that you don't discount the possibility that there's some other reason that they're correlated other than causation. All right, so now we're going to start trying to quantify this linear data that we looked at. So we pointed out that the scatter plot looked very linear before, and now we're going to figure out how is that linear and what is that line. So to do that, head back to your two-variable analysis. So you should all have a scatter plot on your page, and we're going to go ahead and add a trend line. So to do that, right-click on any of the data points and select Add Trend Line. It should automatically select linear, so leave it like that, and just also select the two boxes, Display Equation on Chart And we'll display the r squared on chart. We'll learn what that means a bit later. So once you're done, your graph should look like this. Counselors, can I get you to go around and let me know if anyone's having trouble? Put your hand up if you've got this. OK. So it seems as though everyone, or almost everyone is. Feel free to let me or any of the other counselors know if you're having trouble. So why is this linear regression important? How is it helpful? So we have here this nice equation that tells us that we can find the y value given the x value using this equation. Now this is an approximation, of course, but it can be very helpful for extrapolation and interpolation. So extrapolation is saying I have data between 0 and 1 and 1. If I want to find what the y value should be at 2, I can use this equation to figure it out. And likewise, if I want to find what the y value should be between these 2 points, I can do that. So those are extrapolation and interpolation, respectively. And an example of how this could be helpful is in what I got mentioned yesterday, the speed density curve. If we have information on the speed of vehicles on a certain section of highway at a certain time, and the density on that section, we can take those data, plot them out into a linear plot like this, and assuming that the traffic follows that green shield model, it will form a linear plot, and then we can figure out what the speed should be given a certain density. And that can then be used in analysis of how to reroute traffic to achieve optimal performance. All right, are there any questions so far? All right, so I'm now going to head to another thing to consider regarding this data is how closely they're packed around this line. So I have 3 plots here. And these 3 plots have the same or very similar linear regression. What is the difference between them? So can anyone qualify what that difference is that you're seeing?
They have the same what?
Pardon?
They have the same
Linear regression. So if you add that trend line to all 3 of these, they'll all 3 have a similar trend line. Yes, so trend line and line of best fit mean the same thing in this context. Yes, Matthew? Oh, sorry. No, you're not. Andrew. Right. Yeah, so the last one has the strongest correlation. And what graphically about it tells you that? Yeah. So it looks like a line. It's very closely packed into that line. And I like how you use that word strongest correlation, because that is what statisticians use. They have the same linear regression, nearly, but they're not equally closely packed. So the correlation is said to be weaker in the ones that are more spread out and stronger in the others. Now, how do we figure out, or how do we quantify this? We quantify this using a value known as Pearson's correlation coefficient, and that's called R. Right? Is everyone following so far? Are there any questions? So to take a look at R, before I start babbling about the numerical values, let's experiment a bit. So head over to your 2-variable analysis spreadsheet. Most of you are in it. And you'll notice that we have 4 values up at the top. We have our M and our B. Put your hand up if you know the mx plus b form of a line. OK, so you've all been taught that. So we can actually tell these data, which are randomly generated on the fly, what trend line they should follow. So if you try changing M, we can go, say, to 1, and then the data will update to show this new trend line. And likewise, B, we can change the y-intercept, say, to 0, and again, the data will update to show that. And then this core variable, this isn't any official statistical measure. It's just how much random noise we're adding to it. So 0.02 is fairly small. If we change that to 1, now we have a huge amount of random noise there. but still a similar overall trend line. And we can see the R in the value below that. So when we add that up to 1, R is now 0.43. That's fairly low. If we change it from 1 back to 0.02, R is now 0.99. And that's very close to 1. So what this R value represents is how good of a correlation it is. If it's closer to 0, it means not a very good correlation. If it's closer to 1, it means a very good correlation, as it is in this case. And one last thing to note is take a look at what happens when we make m negative again. What does R do? Right, it becomes negative. So R actually ranges from -1 to 1. And if it's very close to -1, it means a strong negative correlation. If it's very close to 1, it means a strong positive correlation. And one last thing we can try is setting m to 0. Pardon? OK. Setting m to 0. And when that happens, we now have a correlation that's close to 0 because there is no correlation. It's just random noise. And you can hit F9 and reseed that and take a look at what it does there. All right, so put your hand up if you're good on that so far. All right, seems most people are, so we're good to keep going. So here's how we get R. Anyone want to try calculating that by hand? Anyone want to try understanding that? You should be able to, given what we've covered. But as you can see, it's not a trivial calculation to make. And that's why we actually use the Excel Pearson function for most purposes in order to get R. So if you take a look at your 2-variable analysis spreadsheet and this R value, you'll see that that's exactly what I've done. I've entered Pearson and told it to use the values in the X and the Y columns. So I'll get you guys to try just retyping that now. So delete what was in that cell there, that D2 cell, and try it again. So type equals Pearson. And then you're going to select the data in the X column. And it should be down to 50. Then hit a comma and select the data in the Y column. The reason we need a comma here is because it has 2 variables now. Now that we're dealing with 2-variable analysis, the functions often take 2 data sets. Then hit an end bracket and hit enter. And that will calculate your Pearson's correlation coefficient. All right, put your hand up if you've done that successfully. OK, can I get the counselors to go around to anyone who's having trouble and help them out? So let's do a bit of a case study here. This is some. Actually, I'll put this full screen for you.
What do you enter? Pearson bracket A?
Yeah, Pearson bracket A6 colon A50, comma B6 colon B50. So we see here. Can I get your attention, please? We see here a scatter plot of how many lates students in grades 9 and 10 had on their fall term report card versus their average on that report card. So who can tell me something that this chart shows? I've heard from you guys a fair bit. How about Andrew? OK. So it's very clustered around 0. So that tells us that if we were going to do our 1-variable analysis on the number of lates, what kind of a distribution would we get? Maybe draw the histogram in the air. Right. Right. So the histogram would be very skewed towards the right. So it would be skewed with a big bulge in the beginning and not much at the end. Yes?
The mark started at, the peak mark was 81.9%.
Right. So what this tells us is that for students who had 0 lates, the mark would be around 81.9%. So that's not the average. The average is going to be lower than that because not all students had 0 lates. But since most students were close to 0 lates, it's a good indicator of the average. Now, what does the trend line tell us? Solomon? What does the trend line in this graph tell us?
It shows a negative correlation.
Right. And that makes sense, right? If you're late more often, you're probably going to get lower marks. Yes?
It has a negative R value.
Right, exactly. So since it is a negative correlation, our R value is negative. And what does the 0.51 tell us about R? James?
It's got more or less an average sort of
Yeah.
correlation.
Yeah, so the term that we normally use is moderate. So it's a moderately negative correlation between these two. Now, can anyone hazard a guess as to what the cause is? Is it a causal effect? Is it a reverse causation effect? So if your marks go down, you get discouraged and you don't show up as on time? Or is there some common cause that's affecting both? Yeah?
I think it's some common cause affecting both because that's a late of 100 at the very maximum.
Yeah,
I think the
yeah.
common causes, they just don't care.
Okay, so that's a good thought. Any other ideas? Yes?
It's common cause because depends on how hard you study.
Okay, so how hard you study. So if you study more, how would that affect how often you're late?
I don't know. I don't know. That's like the third factor.
Okay. Okay, but I guess work ethic maybe might factor into that. Any other ideas? All right, so we'll take a look at the next one. So you guys are a lot smarter than you and your size 12 shoes. When I first did this study, I thought that it was causal. I thought that students who were late more missed more class, therefore got a lower mark. But then I took a look at the information regarding total time late, not just total number of lates. And we'll see that some students missed 3,000 minutes being late, which is a lot, and most were very, very clustered in the 0 range. And the correlation here is considerably less. I didn't put the R value on there, but it is less. And you'll also note that the trend line is a lot shallower. The scale of this graph hides it, but it's 0.009% here, and it's negative 0.3%, right? So here this indicates that if you're late once more, your mark on average will go down 0.3%. Here it indicates that if you're late 1 more minute, it'll go down 0.9%. The average time being late was 8 minutes. Sorry, 0.009%. So the average time being late is 8 minutes. That means that number of lates is a lot bigger of a factor than time being late. And that can tell us that in reality, it's not causal. It's not because you miss more time and therefore your mark goes down, but that if you're late more often, it's probably because of a common cause of diminished work ethic that causes you to also be less focused on your class. So that's an example of how we can take 2 data sets and compare them and realize that it's not actually a causal relationship. And that's something similar to what you guys should be doing in order to figure out whether your correlations that you observe in your traffic data are actually because of a cause and effect. So, not all data sets have linear scatter plots. So I mentioned that we had the speed density scatter plot would be linear. Given that, can anyone think of a scatter plot that might not be? Michelle, do you have any idea?
The speed volume.
Speed volume, okay, yeah.
Carbon-14 concentration and material decay over time.
Okay, that's good. For those of you who didn't hear, carbon-14 concentration and material decay over time. So you mean time, right?
Yeah.
Yeah. Yeah, so I'm sure you know that that's exponential, but for the benefit of the rest of the class. And yeah, what Kartik mentioned, that we have the other 2 fundamental diagrams that in a green shield model tend to be more quadratic or square root based. such as the flow density. And flow density can change with time. For instance, if there's an incident or an accident or some other slowdown on a road, that will change what the maximum capacity is. That will change other parameters of the road, and that can potentially change this curve. So how do we figure out what the new curve is given some data based on the flow and the density? So I showed it for a second. We can actually take this data and regress it in real time and find the new peak flow and alter things like ramp metering smartly. So that's one example of what an intelligent infrastructure might do using this regression technique. The question remains, though, if we have a scatter plot that looks like this, how do we regress it? A line isn't going to be very interesting. A line's going to do something like this and have a very low correlation coefficient. So the way we regress it is using nonlinear regression. So to do that, we'll head back to our two-variable analysis sheet. And head over to the Nonlinear tab. So what you see initially is there's already a graph made for you, a scatter plot, of x versus y1. So can anyone give me a suggestion as to what type of function might model this data set well? How about you, Andrew? Do you have any idea? Maybe you haven't learned about that type of function yet, so that's not quite a fair question. Senia? Okay, so it could be hyperbolic. That's definitely, and because it's not too long, that would certainly work in this case. In reality, it's a function that's related to a hyperbola, which is, pardon? Exponential. Okay, so it could also be exponential. We notice that it does go down to 0, which indicates that it might not be exponential. This data is actually quadratic. So you guys, or most of you should be familiar with parabolas, right? So now we'll show you how to create a regression curve that is of the form of a parabola. So again, we're going to right-click and add trend line, and this time choose polynomial order 2. So an order 2 polynomial is a parabola. And again, we'll hit to display the equation. And now we can see that it fits these data very, very well. All right, looks like most people have done. Put your hand up if you're good. Okay. Yep, that's everyone. Great. So now we can take a look at some other types of data. So select the red data markers on your chart. And you'll notice that we have two boxes here, one over the x column, one over the y1 column. What you can do is on the edge of that box, click it and drag it over to y2. And you should get this. Okay, so when we have our chart, click on one of the red markers there, and you'll see that some of them highlight in these little boxes. And then you will see these two purple and blue boxes over the x column and the y1 column. Click on the y1 box and drag it over to y2. All right, so I'll show you that again.
Can you explain
click on
what
this.
you did before?
Let's see where you guys are at. Okay, so to get the boxes to show up, I think that's where people are having trouble. What you have to do is click on, I guess you can click on the, no you can't. Oh yes you can. So click on the chart, not on the lines, but on the white space between the lines, or on one of these red data markers. If you're having trouble, it would help to look up at the screen, right? So if you click on one of these red data markers, and these two boxes should show up. All right, so I'm seeing some people are jumping ahead. Put your hand up if you've got it. Okay, so looks like everyone has. If you are still having trouble, feel free to call over Will or Francis. So you should all have something that looks about like this. Now this plot, or this trend line, fits it very well. So it fits these data very well, but there's actually a slightly better one we can use. So I'm going to click on this line and hit delete. So when you click on the line, you'll see the two ends of it have little markers that show up, and if you hit the delete key, they'll delete. And now we'll try adding a different one. So again, right-click on the data and hit Add Trend Line. And this time, we'll choose a logarithmic one. And again, we'll set Display Equation on Chart and close. And this fits the data a fair bit better. And you can confirm that, for those of you who are so inclined, by taking a look at the data. So x is just rand. y1 is a random number, so we're adding some random noise to it, plus a7 squared, or a whatever it is squared. So y1 is quadratic, and y2 is this ln function, the natural logarithm. For those of you not familiar with logarithms, that is a logarithmic function, which is therefore best modeled by 1. So now I'm going to get you guys to spend 2 or 3 minutes trying to figure out how to regress y3. So again, we're going to click on the data set and drag this over to y3. This gives us a much more interesting scatter plot that clearly the logarithmic function does a terrible job of regressing. So